our prize givings.
Great. Thank you, Dominic. Ladies and gentlemen, let me welcome now you to the second part of this celebration of modeling and simulation, and that's the awarding of the Berni J. Alder Cecam Prize. And we are very happy that Berni Alder, after whom the prize is named, is here with us today to celebrate, and he is willing later to introduce the winners of the prize. So the Berni J. Alder Prize is a prize that honors exceptional contributions in the field of molecular and atomistic simulation. I think it's the most prestigious prize in this area in Europe. The prize is given every 3 years, and it comes with a sum of money. It's actually 5,000 euros. And this is, of course, a small sum of money compared to prize like the Nobel Prize, but for an organization like Cecam, that's actually a lot of money. The Cecam Prize traditionally was given at the CCP, the Conference for Computational Physics, which every 3 years is organized in Europe. We have decided to separate it from the conference just to show that this is not just a physics prize, it's a prize that honors contributions from all the scientific disciplines covered by Cecam. For the first time, the prize was given in 1999, and I'm very glad that the first recipient, Giovanni Gicotti, is here with us tonight in the second row. In 2001, then the prize was given to Kurt Binder, in 2004 to Mike Klein, and in 2007, Dan Frenkel received the prize, and also Dan is here with us tonight. In 2010, the recipients were Roberto Cari and Michele Parinello, and the most recent recipients of the prize in 2013 were Hermann Behrensen and Jean-Pierre Hansen. Tonight we have two other towering figures of computer simulation, with whom we will honor for their very important contributions in the simulation of quantum mechanical systems. And that's David Sepperly from the University of Illinois at Urbana-Champaign, and Hardy Gross from the Max Planck Institute for Microstructure Physics. I think we should give them a round of applause. Before I give the floor to Berni, I would like to briefly introduce Berni Alder, even though he doesn't need any introduction probably. Berni was born in 1925 in Germany. Fleeing from the Nazis, he moved to the USA with his family. He studied chemistry at UC Berkeley and then went to Caltech to do a PhD with John Kirkwood. From there, he moved back to Berkeley as an instructor, I think in chemistry also. And then he started working at Lawrence Livermore National Laboratory, and he has had a 60-year career at that laboratory, still working there, if I'm not mistaken. Berni is the father of molecular dynamics simulation, and we have seen today how far this simulation technique has come, what you can do today with molecular dynamics. Berni used molecular dynamics to make important discoveries, including he showed that there is a freezing transition for hard spheres. It's a first-order transition. He proved that using simulation. He also showed that autocorrelation functions of velocity actually decay much slower than expected due to now famous Alder vortices. He also contributed very importantly to the simulation of quantum systems. In fact, he collaborated with one of the prize winners today, with David Sepperly, on the computation of the energy of the homogeneous electron gas, which served as the basis for many other developments. Berni was honored with the Boltzmann Medal in 2001, the most prestigious prize in statistical mechanics. Another recipient of the Boltzmann Medal is hiding in the second row, Dan Frank. In 2009, Berni received the National Medal of Science from President Obama. And tonight he's here with us. I'm very glad about that. It's great that you came all the way from California to be with us here. And could you please now introduce the prize winners? Berni, please.
Let me sit here. Well, thank you very much. The first thing I would like to say is to thank the Cecam medal, the Cecam people, for establishing the Alder medal. I never had an opportunity, this seems to be the appropriate place, to particularly thank Michel Marshall. He is the one, when he was head of Cecam, that worked very hard in establishing the prize. And I'm very thankful for him and the organization to maintain it. So thank you. I think the second thing I want to say is I wish the quantum mechanical many-body problem was in as good a shape as the classical. None of the existing three major methods by which to deal with the quantum mechanical many-body problem is sufficiently accurate as yet. There are three major methods to approach the quantum many-body problem, and the oldest one by far is Hartree-Fock, around 1930, which used expanded the wave function in single orbitals and put these orbitals into a Slater determinant to make sure that we have anti-symmetry. And it has made some progress recently by using the computer random search in Slater determinants to get more accurate results than previously. What we have learned from that method is extremely slowly converging. They now have billions of Slater orbitals, and it still isn't quite as accurate as one would like. That's really the big problem in quantum many-body theory. You need extremely accurate solutions because the chemistry is in the 7th, 8th, 9th significant number. And none of the three methods have achieved that yet. Even the latest developments in Hartree-Fock is not yet accurate enough by an order of magnitude. Now, the three methods, the Hartree-Fock methods, and the other two methods are presented tonight by their top propagators, by their most prestigious workers in that area. And the one that, the density functional one has been largely developed by Hardy Gross. And he worked with the master in the field. He worked with Walter Cohn for close to 6 years, 2 years as a postdoc and 4 years as a prestigious Heisenberg fellow, which was a parking position till the Germans had enough academic positions to place their most talented scientists. Now, Hardy is like most Germans, likes warm climates. No, you know, Goethe used to say a few hundred years ago that the Germans like to go to Italy where the orange bloom, or the oranges bloom. And Hardy found an equivalent place in Santa Barbara with Walter Cohn, which has also a very warm climate, and oranges bloom there as well. Hazen worked on almost all aspects of density functional theory. He's done it for relativistic systems, for superconductors, for high temperature, for pressure. But his most famous work, the most quoted work, is to extend the density functional method to time dependence. And that's the most quoted paper. I'll come back to that in a minute. I like to tell three things about Hardy-Gross, which also matches my attitude to the field. And he calls density functional theory unreliable because it is not really accurate enough. It's a mean field theory which neglects the whole correlations. The other thing he used, I also find the word ab initio, which is primarily used in that field, a little pretentious because all the methods are ab initio. Ab initio just means you put in the charge of the nucleus and the number of electrons, and that's it. And from there you get the results. So ab initio to him means too expensive. To really do it ab initio, too expensive. But the best one of his three sayings that I'm quoting is something that he calls what I call an acronym. It's called FEPU, F-E-P-U, standing for formally exact and practically useless. Many of the lectures that try to, for example, Hardy works not only in density functional theory, but other things as well. Like I read him give a beautiful lecture on the removal of the Born-Oppenheimer approximation, where you calculate non-adiabatic potential energy surfaces. And it has nothing to do with density functional theory. And it's a field where there have been lots of formal theories which are practically useless. Now, David Sepperly, he worked with me for some 10 years. And actually, some of you may not know that quantum Monte Carlo may have actually started earlier than density functional theory. It was started in a little known paper by Mark Katz, a brilliant mathematician who one of the few was also willing to do applied problems. And he did the hydrogen atom by what's called now quantum Monte Carlo, except there occurred a huge problem. Namely, the birth part of the quantum mechanical problem, by the stochastic solution, occurs when the electron comes near the nuclei. And there, of course, the wave function has a singularity. So when you do it by statistical method, all your the whole time you spend birthing processes to get, because to deal with that singularity when the electron gets close to the nuclei. And it was Kalos who really made that process doable by introducing an importance sampling. And Kalos was the mentor of Sepperly. Yes. And the big Achilles heel of classical molecular dynamics is the fact that you don't know the intermolecular potential. I feel very strongly that unless we can do water well, we can never do biology well. You can get qualitative results, but not quantitative. And so that's what drove me to do the quantum many-body problem, to get more accurate intermolecular potentials. And that's still a work in progress. In any case, I brought Kalos out to Livermore, where I worked at the time, for 2 summers to try to explain to me how his quantum Monte Carlo scheme worked. And I sat next to him, and I could never quite catch on. The problem was that Kalos explained things extremely well in detail, but I never got the overall picture. And so when I went to a conference in Corsica and met David Seppele, he could at least explain to me the overall scheme. So I persuaded him to come to Berkeley and Livermore. And we worked for some 10 years. And we produced, the thing we really worked on is the electron gas. He'd done previously the electron gas by approximate methods, and I insisted that we try to do it by a method which we could control the accuracy. And we did, and it is the most quoted paper that he and I have produced. And I want to tell you, first of all, I want to thank the density functional theories for making it such a popular paper, because they don't have the correlation. They were grasping at any problem where they could get the correlation energy, and the only thing that was available was this homogeneous electron gas, which of course is a lousy approximation for the electron distribution around an atom. I mean, it's very, very oscillatory thing. So, but there was nothing better, so they used it. But then they realized also that it was a poor approximation, and then went to what's called a gradient correction. But that's also not very good, and because we once tried to make the correction to the homogeneous electron gas with the gradient correction, and it goes the wrong way. The gradient correction is so large that a simple correction, linear correction, does not work. So in any case, we developed this nodal release method, which does give the exact transitory solution. Exact because the difference between the boson and fermion state is relatively small, and you can project out in this transient estimator, you can project out the fermion solution. Now, I want to just finish up by telling you the vagaries of being the most quoted paper, both Hardy Gross's and ours. There's an interesting story having to do with the most quoted paper in PRL some years ago. When I looked at this, we were the third paper, David Seppele and mine, on the electron gas. First one is the nuclear one by Steve Weinberg. The second most quoted paper was Walter Cohn's density functional theory, and the third was Alder, Seppele Alder. But then I happened to look down further down, and there was a seventh paper, most quoted paper, by a well-known quantum chemist, many-body guy at Purdue. And Purdue's paper we had published the electron gas correlation energy at a series of densities, trying to locate the Wigner transition and the polarization transition of the electron gas. And Purdue's paper was so much quoted because he fitted our paper to a polynomial. So it was much easier for the density functional theory to use our data to get the correlation energy. So it may have been that if our paper and the Purdue paper, which has no intellectual component except that it fit the data. If those are added together, we might have even been first. So with that, I'll turn the thing over to the next.
Well, thank you, Bernie, for these very interesting comments. So, David, would you like to go first now?
Well, thank you very much, and thank you, Bernie, for those remarks. Actually, duplicate some of what I was going to say, but that's all right. It'll be shorter. I want to thank Cecam for this great honor. I want to thank my nominators and the committee for selecting me. I feel very honored that I get a prize with the name of Berni Alder and with the name of Cecam, because both have played a big role in my scientific career. As Bernie said, I was a graduate student at Cornell and also at NYU, and I worked with Jeffrey Chester, who passed away last year, unfortunately, and Mao Kalos, who didn't pass away. He's still alive and kicking. Mao really taught me all about Monte Carlo and all about quantum simulations, and I really were just standing on the shoulder of giants, as Newton said. And also, I really profited from the rise of the computer industry. I mean, I tell my students now that what they have on their cell phone is 1,000,000 times what I had when I started out. As Bernie said, we met in a French summer school in Corsica in 1977. I was just doing electron gas calculation at that time, and a year later, I ended up in Berkeley, and we collaborated for 9 years or so. And what really impressed me about Bernie, which I really learned, was his focus on the fundamental problems of science, and not getting a lot of publications, but trying to get significant ones. And so the publication on the electron gas was it was a remarkable thing that we were able to both introduce a new method to fusion Monte Carlo and provide something for density functional theory, which for 10 or 15 years became a de facto standard. But for me, it was winning a lottery ticket, basically, that it was taken up by the density functional theory and became noticed. Otherwise, I'm sure it would have gone into the usual fate of publications and not so much noticed. The second problem that Bernie and I worked on, he didn't mention this, was dense hydrogen. That is, you take hydrogen and put it at extreme pressures. At that time, we were doing zero temperature, which is not too important except as an intellectual exercise. But we were able to make a couple of predictions out of those calculations. Hydrogen, I should say, is a kind of an ideal playground for our quantum methods, because we could start out from electrons and protons. You don't have a lot of the complications that heavier elements would have. But on the other hand, you have all the subtleties of quantum mechanics in hydrogen. And in addition, it's extremely important, the most common element in the universe. And it's something that's very exciting these days, because experimentalists are actually verifying, or maybe not verifying, our predictions. And just in the last few years, they've discovered several new phase transitions, some of which we predicted. Two of Bernie and my predictions actually were verified, namely the rotational transition in hydrogen at 1 megabar. And we think this year, finally, they saw metallic hydrogen. We predicted 4 megabars, but we had the wrong crystal structures. The experiment sees 5 megabars. So we feel like we weren't too far off. And this work on hydrogen has continued for me for the last 35 years. In fact, even this week in Cecam, two of my collaborators, Carlo Perleone and Marcus Holtzman, were up here, and we were working on the latest twist, namely how to put thermal excitations in and dense hydrogen, and could that have an effect at 5,000 degrees? So, it's still very active, and as Bernie said, not a totally solved problem. Now I want to say a few words about Cecam. It certainly had a big impact on my career. Yesterday I was counting up the number of times I've been here, and I know that it's at least 15 meetings and workshops. I've organized 2 or 3 workshops in at least 2 schools at Cecam. The biggest impact was when Michel Marechal invited me to sabbatical in Lyon, 2001, 2002, and took my family there for the year. And Cecam provided not only sabbatical support, but support for both Carlo and Marcus, my collaborators. And so we had a little group here and working on hydrogen. That's where we developed this coupled electron ion Monte Carlo method that we're still trying to milk 15 years later. I first remember Cecam in the early 80s when going to a workshop in Paris, and I met the indubitable Carl Moser and went to his apartment and met the dogs and the whole bit. And I remember in the 80s running into Carl Moser various places around the world, and it was kind of fun, and coming to the workshops and so forth. During my sabbatical in 2001, I said, well, this is really something we don't have in the U.S. We have a lot of workshops and so forth, but they're not very coordinated in our area of simulation. Of course, you have all the Gordon conferences, but and in talking to Michel, we decided to try to make more American participation, and so for the last 15 years, I've been sending students to Cecam workshops, students and postdocs, and I think that's helped a little bit on the transatlantic communication, and certainly helped the students that I sent in their career and meeting people outside their own university in the simulation world. Unfortunately, that program is coming to an end because of difficulty getting refunded. Anyway, I want to close here on a personal note. As many of you know, that tomorrow is the Thanksgiving holiday in the U.S., and fortunately I've missed all of the Cecam organizational meetings because they're always on Thanksgiving, and that's always a family holiday for me. I grew up in Charleston, West Virginia, and normally I would be going there with my family. But tomorrow my father and my brothers and sisters and all my nieces and nephews will be there, but my family won't be there. I'm lucky to have my daughter here, who's a graduate of EPFL and works across the street at UNL, and so at least we had a Thanksgiving celebration a few days ago. My other 2 children are in the U.S. doing their own Thanksgiving, and maybe they're watching on this streaming. But what we really miss is my companion of the last 45 years, Perry Sepperly, who passed away last year, and she really enjoyed the time in Cecam 2 in Lyon, and she came many times to Lausanne, and we lived here for 1 semester, and so we kind of miss her presence here. So anyway, I want to thank everyone. Thank Cecam for giving me this prize. I really appreciate it, and that's all.
Thank you, David. Bernie has pointed out the scientific achievements of both the prize winners. What I didn't say before is that they have also contributed a lot to Cecam, as you pointed out. Both of you have organized many workshops and schools. You managed this program of the NSF to send students over to Cecam activities. You have acted as a president of the Cecam Council. It's great, and we are really thankful for the activities that you have done for Cecam over the years. May I now ask Hardy to say a few words?
Well, it's a great pleasure to be here, and me too. I would like to thank Cecam for this great honor. And I want to say a few personal words at this point. Not so much about science itself, maybe a little bit about science, but about the circumstances of doing science and things that happened in my personal scientific life. So this is where it started. This is my hometown, Frankfurt on Main. That's where I went to high school and where I went to university. And this is the entrance of the Goethe University. It still looks pretty much the same today. However, when I started studying there, it looked a bit different. When I started, this was still at the time of the student revolution, so during my first semester, in fact, most of the classes were cancelled due to strike. So I had to find some other occupation like this one, so that's myself doing something else. But then fairly soon these student revolts faded away and things got more serious. And this is my first important teacher. In fact, I owe it to him that I became a physicist in the first place. When I entered university, I started studying mathematics and psychology. And fortunately, it was compulsory for math students at the time to take classes in theoretical physics. And those were taught by Rainer Dreitzler. And it was these beautiful lectures that convinced me that, for me, maybe theoretical physics is more interesting than mathematics. And I've never regretted that step. So after the Vordiplom, which is the first comprehensive exam in the German system, I dropped both mathematics and psychology and switched to physics. So I did my diploma thesis and PhD thesis under Rainer Dreitzler's supervision. And for him, the most important motto, one could say, was to always go for the deepest understanding possible. And ever since, I've tried to follow this maxim. Sometimes hard, but I think it's important. Now, it was still in Frankfurt when I was a postdoc that I thought about density functional theory. And this is the theorem that is now known as Runge-Gross theorem, which is the mathematical basis of time-dependent density functional theory. Those are mugs that symbolize the basic theorem these mugs were produced at the 30th anniversary. Now, it was a very fortunate coincidence that in the early 80s, I shared the office with this guy, Erich Runge. He was a master's student at the time. I was a postdoc. And we knew about ground state density functional theory. We knew about the Hohenberg-Kohn theorem, and which I would phrase a bit differently than Berni. So it's as you said, it's a terribly hard problem. It's the exponentially hard quantum many-body problem, many-electron problem. And the Hohenberg-Kohn theorem transforms this into another exponentially hard problem, which is the Kohn-Sham equations. But having rewritten it in this form, it allows you to make approximations that otherwise you wouldn't have dreamed of. This is then a possibility of tackling the many-body problem in a very different way. But it's still ultimately, I agree with you, kind of a mean field theory. Okay, so And here I want to say an important message, that science always depends a lot on the environment. So this was at the University of Frankfurt, and you have to know that theoretical physics at the University of Frankfurt at the time was dominated completely by an experimental facility nearby, the GSI, which at the time was the biggest heavy ion collider in the world. So basically everything, all the seminar talks, the colloquia, whatever people would talk about was heavy ion scattering. Right? So you collide two uranium atoms, and maybe if there's a hole in the K-shell, if this then dives into the negative continuum, you may create positrons. So questions of this kind. Now, it's a many electron problem, after all. But Erich and I, knowing density functional theory, we realized, well, this is certainly not at all a ground state problem. So highly energetic collisions, the electrons are not in the ground state. And there, from this environment, we thought about, well, can we make a time-dependent version of density functional theory? So this is the idea that we had in mind. Colliding nuclei that provide a time-dependent, so classically moving nuclei that provide a time-dependent field for the many electron system. And this was the idea. So now, as you know, time-dependent density functional theory by now has conquered, almost every corner of theoretical physics and theoretical chemistry, even TDDFT for qubits, spin dynamics, all kinds of things. Nothing of this we would imagine at the time. Also, most applications are within the linear response regime, which is also something that when Erich and I thought about it, we certainly did not imagine. I mean, in a heavy ion collision, you're never in the response regime, so it's a totally different thing. Now, it's also a funny aspect that I want to mention, that this problem that we had in mind of classically moving nuclei coupled to the quantum many electron system, that basically only in the last few years, I would say, we are beginning to understand how to do this properly. And one of the big problems that has plagued the community for decades, I would say, is the fact that, well, in the real world, nuclei are also quantum particles. So ultimately, what we really have to look at is the many electron, many nuclei problem as a combined quantum system. Now, often this is not important, but sometimes there's the quantum character of the nuclei showing up, and the nuclear wave packet may split, like in a dissociation, let's say. There's some probability of the nuclei for dissociating, while some probability for the molecule to stay together. So it's a splitting of the nuclear wave packet. And often this is produced by so-called non-adiabatic couplings, where part of the nuclear wave packet moves on one potential energy surface and the other part on another surface. So then, if you want to treat the nuclei classically, the big problem is, what is the right classical force? Is it the gradient of surface number 1, or is it the gradient of surface number 2? And this fundamental problem then led to, let's say, algorithms that were invented out of desperation, like Tally surface hopping, that try to deal with this situation. Now, and this is the point where I couldn't stop myself of saying a few scientific words. So just in the last years, I think there has been some progress. We are beginning to understand how to correctly tackle this mixed quantum classical system. And this is what we have called exact factorization. It shows that the complete wave function of the electron nuclear system can be written without approximation as a single product of a nuclear wave function and a conditional electronic amplitude. And one can deduce equations of motion for each factor, and it turns out that the equation of motion for the nuclear factor is a nice Schrödinger equation. So this is, if you wish, an exact equation for the nuclei, and hence the time-dependent potential that appears in this equation, if you take the classical limit, is the right classical force. So there is actually, and this is the important message, no choices. The gradient of this exact nuclear Schrödinger equation is the correct classical force. Okay, and this then can be turned into a mixed quantum classical algorithm, different versions of algorithm. And there's an interesting aspect to it that if you look at these exact time-dependent potential energy surfaces, they show nearly discontinuous jumps in the presence of what one would call non-adiabatic couplings. So this is indeed reminiscent of Tully surface hopping, but it's not Tully surface hopping, it's just the Schrödinger equation. So this now is what we feel the right way of dealing with classical nuclei. And then still another step is missing, namely the density functionalization of the electrons. Right? So the electronic degree of freedom, this wave function, which is a many electron wave function, satisfies a much more complicated equation of motion. It's not a Schrödinger equation. It involves also the nuclear degrees of freedom. But nevertheless, it can be density functionalized. And if one takes these two things together, the classical motion of the nuclei and the density functional equation for the electrons, then really give you an algorithm of tackling the complete electron nuclear problem. The interesting aspect of this is, and this was not noticed before, is that these equations of motion contain a Berry phase connection, a vector potential type term that characterizes topological features of matter. And it is essential that this is included in this formulation, in particular also the density functional formulation. Okay, so this is the only scientific thing that I want to mention. So it is sometimes, well, a period of 30 years until an additional idea of treating classical nuclei with a many electron problem. Ultimately, one understands how one might be able to tackle it. Okay, so now the proof of this theorem was also very important for me in my personal history, because I presented the theorem on a meeting 1983 in Portugal, and in the audience was Walter Kohn, and he got very interested, and so he invited me to work with him as a postdoc in Santa Barbara. So I moved to this beautiful campus, very warm, yes, indeed. And now, I should say that the fact that Walter Kohn invited me to work with him did not at all mean that he believed that TDDFT was correct. But he got interested in it. And this was, and I understood this only later, that his motto in doing science was even worse. So Reinhard Reitzler insisted on the deepest possible understanding. Walter Kohn insisted on that as well, but one should understand the thing in three radically different ways, in the deepest possible way. So this is even much harder. So that's why it took him also about 3 years or so until he was convinced that TDDFT is all right. Okay, so this is one of the things that I enjoyed most in my life the discussions with Walter Cohn, and as was mentioned before, I spent in the end 6 years working with him in Santa Barbara. Now, one of the things that I want to emphasize is that there are many different ways of doing science. So some colleagues of mine that I appreciate very much, they are happiest if one locks them up in a box and then that's where they produce theorems, let's say. That's not at all my way. So I need communication. For me, this is the number one most important thing. In fact, I have most ideas while talking to other people. And sometimes, after a long conversation, some people say, well, how come you knew all this? And then I frankly say, I didn't know it before we started talking. It just was generated by the conversation. So, for me, communication is the number one important thing. And Walter Cohn, in fact, felt exactly the same way. So I remember an interview that is somewhere online where the journalist asked him what he would do if he was in solitude on an island, but with access to all libraries and all the knowledge of the world. Would he do science? And Walter said, no, definitely not. The main thing is communication. So I felt very much in resonance with Walter on this. And so it is important to create an environment where this communication is possible. And after Santa Barbara, I moved on to the University of Würzburg, where I stayed about 10 years, and then to the Free University in Berlin, and from there to Halle. And in all these places, I found it an important aspect to create an atmosphere of open and fruitful communication. And this is also a point that I want to mention in the context of Cecam. So this takes me to my association with Cecam. I came to Cecam relatively late in my career, and this probably is due to the fact that, well, my first scientific topic, relativistic heavy ion collisions, was not so much on the agenda of Cecam at the time. So my first Cecam workshop that I attended was in 1994. It was on systems in strong magnetic fields, and it was the tradition at the time, a workshop of 2 weeks, and I enjoyed it tremendously. So I attended many others and also organized several myself. And then after a few years, I became representative of the DFG in the Cecam Council, and also I became at some point president of the council. Now, here I want to tell another story. So at the time when I first came in contact with Cecam, it was at the École Normale Supérieure in Lyon. And I remember until today, at this session in the council, when Dan Frenkel asked me if I would be willing to become the next president of the council. He was president at that time. And I remember exactly the phrase that you said. So you said, it's a very light job, you know. You just once a year you chair this important session where the money is distributed, and that's it. But fair enough, you added a little sentence that said, unless there's problems. So I became president, and unfortunately it was at the period where there were problems. So that was at the École Normale in Lyon, where, how shall I say, there were administrative problems that ultimately resulted from a collision of French law, or maybe a strict interpretation of French law, and its collision with the rules of EU funding administration. So these were serious problems, and at the time then the Cecam Council decided to make an open call and for Cecam to move elsewhere. And there were a lot of applicants, many institutions applied, and very many really enthusiastic applications. And there was a committee formed. It was sometimes called the Gang of Four. Some of them are here. Claude Gay, Paul Durham, Jean-Paul Reichardt, and Giovanni Cicotti. And this committee was sent around to check some of the best applicants. And it was a wonderful job. So you were treated like kings, you know. I was there too. Yeah. It was just wonderful. And so in the end, we gave a report to the council, and then there was an election within the council, and as you know, Lausanne made the race, and I think it's been a great decision at the time. So Cecam is thriving here in Lausanne, and at this point I just want to thank well, all those people who over the years have communicated with me. First of all, my family and my group in Halle, who have been the main victims of this communication. That's my group a couple of years ago. And well, I want to thank Cecam for providing this marvelous environment. Thank you.
Well, thank you, Hardy, and thank you all the speakers for these very personal and also inspiring remarks. Very interesting. We now come to the most glamorous part of this celebration, namely the awarding of the prize. May I ask you, Berni, to do that? To give them the prize winners the prize. So maybe you go first.
I guess. Just one. Yeah.
Your other one is, well, you give them to him. Let's do it. Thank you very much. Dominic, would you like to say something?
Yeah. Well, that brings us to the end of our formal proceedings here this evening. And I would like to invite you to come and join us for a drink and some snacks in the Kopernik, which I believe one simply runs to the top of the stairs and turns left. And you should be there within a matter of meters. Yeah. And that's right, don't turn left. We run to the top of the stairs and turn right, and that should get you to the Kopernik. And I just want to say a huge thank you to everyone who's been involved in this evening. I won't spare anybody's blushes. I particularly thank you to Berni for coming to give out the prizes, to our two prize winners, to Christoph and the others who are here. But it would be remiss of me if I didn't really thank the staff at Cecam, who've worked themselves very, very hard in order to make a great day. So I particularly want to thank my deputy, Sarah Bonella. I'd like to thank Caterina Mendonca. I'd like to thank Marianne Robinson. I'd like to thank Natalie Carmenetti. And I'd like to thank Bogdan Alexandru and Guy Biron, all who worked very hard to make a great day. So could we show our appreciation, please? and we'll see you in the Kopernik.